Let's look at a simple example. Suppose on a wiki article about ice cream, and people have different opinion on what is the best ice cream flavor. Is it chocolate, vanilla, or strawberry? There are 6 possible configurations of opinion. Let's say 3 of them received some votes, and there are 9 votes altogether. 4 goes to chocolate better than vanilla, better than strawberry. 3 goes to strawberry better than vanilla, better than chocolate. And 2 votes goes to vanilla better than strawberry, better than chocolate. Alright, so let's see what would happen with plurality, border count, and counter-share voting, respectively. By plurality voting, it's quite clear. Okay? We will get C as the top one. Chocolate is the best. And then strawberry get 3 votes, putting it on the top, so get strawberry. And vanilla got 2 votes, putting it on the top, so we get vanilla. But as you can see that this somehow does not utilize the fact that chocolate also get 5, which is more than 4 votes, placing it at the bottom. Because we only care about the majority count of the top position, not the rest of them. Well, what about positional voting? Let's say border count. So we have to give some points. There are 3 candidates, and therefore the top candidate get 2 points, then get 1 point, then get 0 points. So chocolate gets 4 votes, in which it gets 2 points. So chocolate get 8 points in altogether. Strawberry get 3 votes where it gets 2 points, so that's 6, plus 2 more votes where it get 1 point. So it also got 8 points. It's a tie. And vanilla got 4 votes with 1 point, 3 votes with 1 point, and 2 votes with 2 points. So you got 11 points. And therefore, vanilla is better than strawberry equals chocolate. They're tied. What about counter-share vote? Let's look at a pairwise comparison here. So suppose we look at C versus V, chocolate versus vanilla. Chocolate is ranked higher than vanilla by 4 people, but vanilla ranked higher than chocolate by 5 people. So vanilla wins chocolate. Now what about let's say strawberry or vanilla now. So strawberry is voted better than vanilla by 3 votes, but vanilla voted better than strawberry by 6 votes. So vanilla better than strawberry. Now what about the last pairwise comparison? We need chocolate or strawberry. So chocolate is voted better than strawberry by 4 votes, but strawberry is voted better than chocolate by 5 votes. So strawberry wins chocolate. Well, it turns out that in this case, counter-share voting doesn't lead to a cyclic output. We do have a logically consistent result, which is vanilla is the best, better than both, and strawberry is then in turn better than chocolate. So these are the 3 different results. First of all, they're all different, and perhaps very disturbingly, majority vote and counter-share vote, both are very intuitive systems, give us completely different results. They're diagonally opposite. Majority vote says chocolate better than strawberry, better than vanilla. Counter-share says vanilla better than strawberry, better than chocolate. And border count then gives you something different. Shows that even when all 3 have some meaningful result, the 3 results can be so different that we don't know which one to pick. Now this is a very simple 9 voters, 3 candidates system. Imagine what would be if it's even there are more choices. Now you might object. First, this is a synthesized example. Maybe in real world it wouldn't be like this. Well, true, this is clearly synthesized to be a small example yet illustrate potential issues. But then again, there are many such paradoxes. This is not an isolated incident. And finally, how would you describe a typical real-world scenario? This is real-world enough. Well, maybe we can start with some simple statements that we all can buy in. We all can convince ourselves they should be true, and then look at the logical implications. We call that the axiomatic construction. So axioms means that these are propositions we take to be true in order to look at the implication of logical conclusions coming out of them. There will be a few axiomatic systems we go through, including in today's advanced material, a Nash's axiomatic system for bargaining, which leads to a unique positive result, and also in Lecture 20, axioms for fairness evaluation. But before then, we look at a very famous axiomatic construction by Arrow. So Ken Arrow in 1950 said that maybe we can all agree on the following 5 statements, and then we can see what implications come out of that for voting systems. The first statement says that each input list should be complete and transitive. All right, fine. We assume complete, even though incomplete input is often the reality in real systems. But let's say it's complete. Of course, we want them to be transitive, otherwise it's logically inconsistent. Second, output list should be complete and transitive too. Fair enough. Third, output should not be just identical to one input list no matter what the other input lists are. Again, fair enough, otherwise you have a dictator. Then there is no point in voting anymore. And then the fourth one says, so-called Pareto principle. If all the input list says A should be better than B, then the output must also say A better than B, because there's no disagreement among the inputs. Finally is what's called IIA, independence of irrelevant alternatives. It says that between a pair of choices A and B, okay, each input's preference between A and B remains the same. Some say A is better than B, some say B is better than A, it doesn't matter. Okay, as long as the preference relative between A and B, a pairwise comparison, remains the same, then even if their preference involving other candidates, like C, moves around from here to here to here, the output preference between A and B remains the same. Okay, because where C lies is irrelevant to A-B's comparison. A is still better than B, and B is still better than A in different people's minds. So the output decision between A relative to B should not depend on where C sits. Independence of irrelevant alternatives. All right, all 5 statements sounds fair enough. Okay, we can say, all right, I can convince myself that all should be true. Then we think, what kind of systems would satisfy all 5 axioms? And the surprise is none. 0. No voting system can satisfy all 5 axioms as soon as there are 3 or more candidates. Again, if there are only 2 candidates, life is easy, because comparing scalars on a real line is fully ordered. This is the famous Arrow's impossibility result that says it doesn't matter how many voters there are. If there are 3 or more candidates, then no voting system can satisfy all 5 axioms that we just believed to be all reasonable. So something's wrong. If a surprise factor is used to judge the elegance of a result, then this is one of the most elegant results that we're going to see in this course. Somehow our intuition isn't quite right. Which axiom gave us the trouble? Not the first 3, because they really define what a meaningful logical voting should be. So it must be either Pareto or IIA axiom. It turns out that it's the IIA axiom. Usually the axiom that takes longest to describe is the first one you should suspect giving you any trouble. The fact that these 5 are logically inconsistent among themselves, that's what negative impossibility results by Arrow says, is due to the fact that these seemingly irrelevant alternatives are not irrelevant after all. Where other candidates sit relative to A and B actually should make a difference in the output. Without that, you actually can have transitive inputs and yet cyclic output. In other words, axiom 5 can preclude the existence of axiom 2. Now, we won't have time to go into the details of the proof of that, But we will go through in the next video segment another impossibility result by Sun, and we will see that indeed these seemingly harmless, irrelevant alternatives are not irrelevant in the final voting after all. In other words, by compressing many lists into one single list, we need to know not just the relative position pairwise, we actually need to keep track of the scale and the position of all the candidates. So sometimes people quote Arrow's impossibility result to say that voting is flawed. Well, that argument actually is logically nonsense. What it says is that our intuition is flawed. Okay? We cannot assume that these alternatives positions are irrelevant. They are relevant. And indeed, later researchers such as Saari have developed possibility results by modifying this IIA. For example, the so-called intensity form that says not only I keep track of relative comparison pairwise between A and B, but also I write down the number of candidates that's in between A and B, which could be 0 or 1 or some number up to n minus 2. We call that number the intensity of A better than B. Then, if we replace IIA by the so-called IIIA, 3 I's, okay, that says that the ranking of a pair of candidates depends only on their relative position and the intensity value. It turns out that suffices to lead us to a possibility result. We don't need to keep track of who, but need to keep track of how many candidates are there in between A and B. Well, then, if it's possibility result, then give me a voting system that is indeed going to satisfy all these axioms. It turns out position voting border count can do that. Okay. So people often ask, what is the true intent of the voter? Are we capturing that? Well, the true intent of the voter is already captured. That's the entire set of input lists, the input profile. That is the true intent. If you want to condense all that into a single list, some information will be lost. What this possibility and the Arrow's impossibility results highlight is the need to count, not just to order. We need to know the scale more than just pairwise relative positions.